SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. So, today we will go to the lecture number 5 of first week, that is the module 1. The topic of the lecture 5 of this subject is structural loading and reactions. So, let us first discuss some of the concept we will be covering in this lecture. Initially, we will understand the unit of the force, and then the two of the typical load component, and which is very popular or very important in our structural engineering. The concept of those will be discussed. One is concentrated load and another one is uniform distributed load. So, our learning objective of today's discussion and this lecture will be, we will try to understand what is the structural loading and try to translate the physical parameters of any particular the building or any particular building element to a structural loading. And the second one is we will evaluate the support reactions due to the concentrated and the uniform distributed load. So, the previous lecture, in the lecture number 4, what we have covered is the different type of the structural supports and their redundancy and their unknown equations, unknown reactions and all. So, which will be definitely take into this particular lecture also to evaluate the support reaction. So, let us go to the first one, the concept of the unit of the understanding the unit of the force. So, what is a force? Everybody knows force is defined as the mass into the acceleration. So, suppose a 1 kg of mass is under a 1 meter square 1 meter per second acceleration, then I may say that is equivalent to 1 Newton force, and 1 Newton is the unit of force in SI, the international standard unit. So, now let us see that what is the actual how much is the particular 1 Newton means. The 1 kg in 1 meter per second may not gives us the real picture of the 1 Newton. So, then 1 Newton is how much kg if it is having a kind of acceleration due to gravity, that is g, that means how much is the weight component of the 1 Newton I am going to find out. So, as I know that the acceleration due to gravity is more or less 9.8 meter per second, then I may multiply instead of the acceleration due to gravity as 9.8, and 9.8 is very close to 10. So, I thought of putting that as a 10 meter per second. So, the 0.1 kg if I put over there instead of the kg and the question mark, then that 0.1 into 10 will be give you something like your this particular. So, instead of how much is the kg, that we may have, this is 0.1 kg. So, that gives you the 1 unit over here. So, that means the weight of 0.1 kg, weight of 1 kg, remember that weight means it is due to the gravity, is equivalent to 1 Newton. Now, what is 0.1 kg? 0.1 kg is nothing but 100 gram. The 100 gram of weight is equivalent to your almost of your the 1 Newton. So, if you take a 100 milliliter of water, a Bisleri bottle of water, 100 milliliter, which is a smaller version of the Bisleri. So, as 100 milliliter of the water is equivalent to 100 gram, because the density of water is your 1000 kg per meter cube or 1 kg per liter or 1 gram per milliliter. So, that means that 100 gram of that particular one small Bisleri the weight is equivalent to 1 Newton. So, please remember that is 1 Newton almost. So, in this point, so we will understand the 1 Newton, and now let us discuss how much is the 1 kilonewton. 1 kilonewton is 1000 Newton, and from that point of view again I do the recalculating these things, and finally I find it is almost about the 100 kg, because again I am multiplying with the g and this 9.8 converted to 10 and all. So, I am finding out how much is the kg, this is 10. So, this is 1000. So, the 100 kg, if I put 100 over here 100, then this will be going to have 1000 Newton. So, I may say that its weight of 100 kg, 100 kg is 1 kilonewton, because kilonewton is very much used in our structural engineering for converting to some kind of a load or so. So, 100 kg is how much? 100 kg is almost like 2% of almost total weight is of course about, I mean these 2 persons having maybe little bit more weight, but tentatively a person weight, one person's weight is 40 to 60 kg. So, 2% equivalent weight is almost about 100 kg, and that is going to be equivalent to 1 kilonewton or so. So, that way initially we covered the unit of the force also for the typically. Now, let us consider some kind of a concentrated load. How a concentrated load can be conceived in practice? Suppose what is this? This is a kind of a hanger where the cloth can be hanged with some kind of a hanger or so. So, in this particular beam, which is the topmost the rod or whatever the metallic rod is under some concentrated pointed load due to this hanger, and this particular kind of a the hook is there, and that kind of a give you some kind of a exactly pointed load on the particular point. Suppose this is a particular small truck, a small very mini truck kind of a thing which is loaded as you know. So, what I have written over here, suppose the self weight of the truck is 1200, that is 1200 kg, and this truck is carrying some LPG cylinder which is having almost about total weight is almost 3.4 ton, and 1 ton is almost about or equal to 1000 kg, that is the British ton, not the American ton. So, if this is so, I may say that the total weight of this vehicle including its self weight plus the other the LPG or cylinder weight is 1200 is your self weight, and this is the additional LPG weight also. So, 4600 kg is the total load. So, then the load on the 4 wheels is almost about 46 kilonewton, because why 46 kilonewton? Because as you know the 100 kg is equivalent to 1 kilonewton. So, I just want to remove these 2 zeros, and then the 46 kilonewton is the equivalent to 4600 kg. So, that is the total load on the 4 wheel, and then the 1 wheel must be take almost what if I assume that everything is uniform. So, that divided by 4, that is 11.5 kilonewton. So, each tire or each wheel will take care of 11.5 kilonewton load, and this is also a pointed load. Why this is a pointed load? Because see the finally the load transmit to the road by virtue of this particular point which is a tangential to the wheel or the tire. So, this is this way we can find out the what are the total amount of load in kilonewton by virtue of some real life example or those kind of things. So, we will translate these things to our the building exercise also. You see this is a 3-dimensional photo of figure of a beam which is 2 beams practically red color, which is called as a secondary beam. The dimensions of the beam is little less with compared to the other the big one yellow color beam. So, those are called the secondary beam, and the secondary beam will transfer the load to the primary beam, that is the yellow color beam. So, reaction of the secondary beam will act as a pointed load to the or a concentrated load to the primary beam. So, something like this is going to be happened. So, and after that particular transferring, and the other loads also definitely will be there in the primary beam will take, and the reaction of the primary beam will act as a pointed load to the supporting column which is mentioned over here as a blue color. So, this way that load will be transferred from the secondary beam to the primary beam and from the primary beam to the supporting column also. We will put the discussion into much more detail when we will go to the 4th week of our lecture, when we will discuss among the loading and the grid pattern and from for a building and how the loading is going to analyze and that. So, this is again that simply supported beam as I have shown, and I have put mark or put two such pointed load, one is 10 kilonewton. So, 10 kilonewton is almost about your 1000 kg, and another load is 4 kilonewton, which are having a kind of separated distance of 1 meter and 2 meter from the left hand side support A. Now, my question is, I have to find out the reaction at A and reaction at B. So, as these particular forces are in all are downward in nature, that is in the towards the negative y axis, and the reactions are of in the positive y axis. So, I must first write down the sigma f y equal to 0 equation, where the R A and plus R B must be equal to 10 plus 4 14, otherwise the beam will be unstable, beam will be translate in the other the upward or downward direction. Now, the second criteria is to find out the exact amount of the R B if I take the moment about R A and put it equal to 0, because as it is a hinge support, as you know this is a hinge support, and we have discussed in the fourth week lecture, for the fourth lecture in this particular week, that the hinge support cannot take any kind of moment. So, I will put this M A at A equal to 0, and that gives me, so M A equal to 0. So, this force R B is having a distance from A is 6 meter. So, the 6 into R B I have put, and then the other loads are of 10 into 1 meter and 4 into 3 meter. These two are added. I am sorry, this instead of this sign, this should be, these two should be added. If these two should be added, then the total moment one side is 6 into R B and another side is 10 into 12, sorry 10 plus 12, that is 22. So, if I now equate this, I will get the R B as 3.67. So, R B is 3.67 is 22 by 6, this 3.67 kilonewton, and R A is remaining after whatever the R A should be plus R B equal to your 14. So, 14 minus 3.67 is 10.33. So, I can find out the both the reactions because of, so there may be some other loads also, So, if I know the value, if I know the distances, I can again put this particular change this equation. So, 2 more load will increase this and those equation will going to change, and finally, we can have some different values of R A and R B. So, this is the way we can find out this is one of the example. Now, let us conceptualize the uniform distributed load. Uniform distributed load, before we conceptualize that one, let us have a brickwork, a brick wall, and let us imagine that this brick wall is having 4 meter of length, and the thickness is 250 mm and height is 2 meter. So, this is your 4 meter, this is your 2 meter height, and the thickness is your 0.25 meter or so, 250 mm. And as you know that if you put the density of the brick machinery as 900 kg per meter cube, I can easily find out what is the total volume. First 4 into 2 into 0.25, that is 2 meter cube, and also the weight, because if I multiply the volume into density, this is the volume into density. So, I can find out the total weight, and this 3800 kg is the total weight of this particular the brick machinery. So, I can say that instead of 2 zeros, if I remove, then almost it is equivalent to 38 kilonewton is the total weight of the machinery. Similarly, I have computed for the RCC, same almost equal of kind of a RCC work, 3 meter length, 2 meter height and 150 mm thickness. So, the volume is 0.9 and the weight is 2250, because the density of RCC is 25,000 kg per meter cube. So, the force equivalent to that is almost about 22.5 kilonewton. So, like that we can actually going to convert, if I know the density of the material, dimension of the material, the total weight, and that change to the total force. So, now here we have a kind of a RCC beam, and this RCC beam is supported in 2 columns, which is in blue in color, and then this RCC beam cross sections is given as 300 mm by 500 mm, and this is having a span of 5 meters. So, let us see what happened is that, because now what I am going to do is that I want to find out the what is the uniform distributed load because of that beam is placing over there. So, what I will do, I will take 1 meter of the length, 1 meter, please remember this 1 meter of the length of the beam, and I will try to find out the volume and the weight. So, the force due to the RCC beam of 1 meter of the length is, the volume is 0.3, why 0.3, because 300 is the cross section, one dimension, into 0.5, why 0.5, because 500 mm is the another dimension of the cross section. So, those two gives me the area of the cross section, and 1, why 1, because the length of these things is 1 meter. So, 0.3 into 0.5 into 1 gives me 0.15 meter cube is the total volume of the beam of 1 meter length, and this is uniform, this volume is uniform throughout the each 1 meter length of the running length of the beam. Now, I multiply that with 25. Why 25? The density of the RCC is 2500 kg per meter cube, which is equivalent to 25 kilonewton per meter cube. So, if I just multiply with 25, I can directly find the force in kilonewton. So, 0.15 into 25 is 3.75 kilonewton. So, that means this particular beam is having a load intensity 3.75 kilonewton per meter length. So, it has 5 meters, so I have to multiply 5 times whatever. So, per meter length it is 3.75. So, I can also write in this form that this is under a uniform distributed load. So, load are uniformly distributed from point A to point B over the span of 5 meter with a intensity of 3.75 kilonewton per meter. Now, from that point of view, how can I find out this R A and R B? So, I can say that instead of putting all over, I can imagine this particular beam is having no load, but a concentrated load of 18.75 kilonewton, which is acted at the middle. Why 18.75 suddenly? Because 18.75 comes from the total R A plus R. Total load of this particular thing is that this is 3.75 kilonewton per meter, and there is total length of is 5 meter or so. So, if I multiply 3.75 into 5, then this is in kilonewton per meter, and this is in meter. So, meter gets cancelled. So, finally, I will get 18.75 kilonewton as a the total load, and that is acting over here at a distance 2.5 meter from A. So, I may say that now sigma Fy equal to 0, then R A plus R B must be equal to 18.75 total load, and the M A is 0 because it is a hinge end. So, now the reaction this R B into 5 this way, it is moving like this, and it must be equal to the moment of this is 18.75 into 2.5. This 2.5 is nothing but the 5 by 2, this total length is 5 by 2, because if it is uniform distributed load, we can assume that this 18.75 which is total load is acting at the center of gravity of the total loading, that is the center point of the total span. So, by virtue of this understanding, we can now find out the reaction R B at as 9.375 kilonewton, and R A is also 9.375 kilonewton if I go with that. So, again I have considered another example where there is a RCC beam of similar nature, the last example 300 by 500 mm, but there is the red color brick wall is also there, whose dimension is 4,500 millimeter in height and 250 mm in thickness, and densities of this the RCC is 19. So, I can easily find out how much is the total weight of the 1 meter length of this particular wall. So, that I have found out this 821.375. Again I will write, I will explain this 4.5 is this 0.45 4500 mm gives me the 4.5 meter is the length, one dimension, 0.25 is a thickness. So, this thickness is 0.25 and 1 is this 1 meter. So, I have taken all the 3 dimensions for this. So, I found out the volume. After found out the volume, I have multiplied that with the density. So, I got this is. So, total weight is now the total UDL stands for uniform distributed load, is now 3.75 is for the beam and 21.375 is for the wall. So, this is the total weight of this thing. Next is again this is under this particular 5 meter of the length, and this is this thing, this total weight is total uniform distributed load intensity is 25.125, and again I can compute. See, I have again found out the total load in multiplying by the 5. So, this is the total load, assuming that total loads acted at centrally, and I found out the moment at A equal to 0 with this equation like previous slide, and finally I come down that down to that this is the total moment, balancing moment, and this is the reaction force at B as almost 62.8 kilonewton, and the RA is also computed. So, like that we can find out the what is the intensity of the UDL from the nature of the building element, multiplying the density with a unit length of that particular element, that volume, and the UDL can be. So, this is another example. So, this is now very easy. If you we show the UDL as this half circles, series of half circles. So, total 10 kilonewton per meter is the intensity of the UDL from A to B. It is a simply supported beam, and RA in equal to RB equal to 30 kilonewton is very easy, because it is a very simply supported beam and a symmetrical kind of a beam. So, the RA must be equal to RB, and total intensity of the load is 10 into 6, that is 16 kilonewton. So, 30 will be the share of this thing. Another example, I put a kind of a particular load UDL, which is your 24 kilonewton per meter at a smaller distance of almost about 2 meter at a almost centrally located, 1 meter from the left and 3 meter from the right support. So, here you see the total load is 24 multiplied by 4, 24 multiplied by 2, that is the total load to 48 kilonewton. So, RA and RB must be equal to 48, RA and RB equal to 48. Now, again I take the moment at A equal to 0, that means from here I am taking the moment, the first RB gives me like this moment, the anti-clockwise kind of a moment, which is RB into 6. Why 6? Because 3 plus 2 plus 1 is the 6. So, RB equal to 6 must be equal to the load, the moment due to this load, and this load, the total load is 48, is acting at the center point. So, this is suppose 48 acting over here. Transfer that particular UDL to a pointed load at the center point. So, this is your 48, and this is why it is 1 plus 1, because this acting see the point of acting of 48, this is 1 meter and half of 2 meters. So, this is another 1 meter. So, 1 plus 1 equal to 2. So, 48 into 2, 96. So, RB equal to 96 by 6 is 16 kilonewton, and RA is equal to 32 kilonewton, that is 48 minus 16. 48 is the total RA plus RB. So, like that we can easily find out the reactions for the UDL, any kind of UDL is placing anywhere in the particular beam. So, this is another example where I have put some UDL also, different two type of UDL, little the left side UDL of 1 meter from A is little heavy, it is 18 kilonewton per meter, and the right side 2 meter span of UDL with B is little the light kind of UDL 6 kilonewton, and 9 is the concentrated load at the particular point. So, let us first find the first equation of this, the Fy equal to 0. Here this you see the RA and RB must be equal to total downward load. So, total downward load I will first can get from this 18 and this 6 and also from the 9. So, 18 gives me 18 into 1. Why 18 into 1? 18 kilonewton per meter is the intensity over a length of 1 meter. Now, 9, this is straightforward, and this is 6 into 2. Why 6 into 2? 6 is the intensity of the load over a distance of 2 meters. So, that is why 6 into 2. So, that is 18 plus 9 plus 12, which is equal to your 39 kilonewton is the total downward load. So, R A and R B, here I have written R V A and R V B, both should be equal to your this 39 kilonewton. Now, this again I will take the moment from the A. So, moment from the A, if I take the moment from the A, this force goes through that. So, this force will not create any kind of a moment. Moment will be created by R B, which is 6 into R B, like this, and rest all are clockwise. So, this 18 into 1 is acting at a distance of 0.5 meter. So, this is that, and then the 9 into 1 is also 9 into particular 1, because it is 0.5, because it is at a distance of 0.5 from here, and 16 into 2 is your 12 total load, and it is at a distance of 5 meter, because 1 plus 3 plus again 1 is your 5 meters. So, 78, and finally, we come down to the R B and the R A as 13 and 26 kilonewton per meter square. Kilonewton only. So, like that we have some other examples also. So, from this particular plate we can have some UDL, which is overhanging kind of a scenario, where R A plus R B is given, like the total load is also come out to be the 81, and again I am taking the moment about A, which is gives me moment about A, means from here it is 5 into R B into 18 into 4.5. Why 18 into 4.5? This is 18 into this is total is 4.5, because 2.5 plus 2, and this distance, if you please read from here, center point of this is 2.5 plus half of 4.5. This is half of 4.5. So, that gives me the equation, and finally, I come down to the R B and the R A. This is also next, where I have put a little around little another way around the what should be the value of this P, this particular force P, that gives the reaction at B equal to 0. So, reaction at B equal to 0 means, if I take the moment at about this, so this is 0. So, the moment because of this 4 kilonewton per meter must be equal to this moment. So, if I equate this to 4 into 7 is that, because 7 is 5 plus 2 is 7, and from here the center point of this load is your 3.5 meter. So, this is that must be equal to P into 2. So, I can find out that this R A in that case will be your 77 kilonewton, and the value of P is 49 kilonewton. So, like that we can do for the simply supported beams. Of course, the other beam was the cantilever beam, the overhanging beam. So, in the cantilever beam I have put some photograph, where you see this is the fixed end and this is the free end. So, the fixed end and the free end. So, this is suppose another cantilever beam. In the cantilever beam also there are some loading, we can see this is one of the loading pointed load, and this is the uniform distributed load, like that. So, those can be also taken in the cantilever beam also. So, something like that can be visualized as a cantilever beam, and there are some of the Astra Tower Hamburg. It was constructed in 1971, where there are the cantilever beams are going on. So, we can have those cantilever beam equations also, or we can find out the R A and R B. Here there is only one reactions R A. So, the sigma F I equal to 0 gives me 20 into 5, because this 20 an entire 5 meter length is. So, this is the 100 is the reaction force, and the MA I can find out 20 into 5 into 0.5 into 5. Why 20 into 5? The loading is 20 into 5, and this is the distance at the center point, half of the 5 meter. So, that means the moment at A is your 250 Newton per meter, because as you know the cantilever beam there are two unknowns, one is the reaction at A and another one is the moment at A, or the fixed end. Similarly, I can find out for that also, it is also very simple. R A is just adding up the forces 12 plus 10 into 2, that is 32, and M A is similarly I can find out the 10 into 2 multiplied by this 2 into 1, because 2 plus half of the 2 is 1, and this 12 into 6 y 12, and this acting as a distance 6, so it is 132 kilonewton per meter. So, I have taken the reference for this particular discussion on this particular two books. You can go through these two books, and also I have let me conclude the lecture today, as we have estimated the exact loading on the structural and the how it is essential for the structure. The type of structural loading also depend upon the material and the dimension density of the parameter, that also has been understood. The support reactions depends upon the type and the placement of the loading, that is also we understood from our lecture. Now, next is let us go to some homework. So, the homework one is, suppose a particular boy is going with a bicycle, and this in a 6-meter span, this thing in a bridge kind of wooden plank kind of a thing. So, I have given the weight of the boy, I also given the weight of the bicycle. So, you have to find out the, and distance between the wheel of the bicycle is almost about 1 meter. So, you have to find out the what is the reaction at these two support when this boy is 1 meter away from the one left hand support. And also you plot a graph to show the changes of the left and right suppose reaction. Suppose boy is moving from the left support to the right support. So, how the changes of the reaction at A and reaction at B, reaction at A and B means A is here and the B is at the other end, how it is going to change, you have to plot it through a graph. I have another kind of a this thing. So, I have some typical profile, two profile of wall. So, there is a cut, and this is a triangular kind of a wall, and the wall dimensions all are given, and the thickness of the wall is 250 and density of the wall material is 200 kg per meter cube. So, you have to finally find out the what are the reaction in A and what will be the reaction in B. And finally, another small problem of the cantilever in the beam, and the loading is given, find the reaction at A and B for these things, and what should be the intensity of the additional UDL within the BC. Suppose what should be the additional UDL I should put in the BC, that the reaction at B will be 40 Newton, will be 40 Newton. So, that also you have to find out. So, those three, I think that is the end of this lecture number 5. Actually, it is lecture number 5.